Today I want to talk about value of quantum Hamiltonian. Quantum Hamiltonian is used as different kind of particles like Fermion, Boson, Boson, and Axion. Symmetrical statics graphs are things like that look like this. Sometimes under the Bloch sphere's control, the Fermion's value can change. If there is no Bloch sphere, then it is totally symmetrical, like that looks like this. Well, when there is a Bloch sphere, this part looks something like this, much extended, stretched looking. And the blue one can be like this. So this is what can happen if the Bloch sphere if the Bloch sphere gets involved in the Fermion, Boson, and Photon and Axion and those kind of particles that can be involved in the quantum Hamiltonian, the Bloch sphere can affect those Fermion, Boson, Axion, and Photons. So the exchanging value can be represented as psi of d over d, and then there will be capitalized wave function and psi of nx comma t. Values of different, so these are one type of something called Fermion. Fermion are these are the graphs that can be explained to Fermion symmetrically, and when we're talking about about bosons, there is the psi of nx comma t, and with that we can have different value and basic bosons, static, and these are in graphs as of course the things change. So this is same as the Bloch sphere, but this one doesn't get like this Fermion, but it rather gets and looks like this. Red will be here, orange will be here, and blue, and then red will go on like this. And this will go up to infinity. This is what can happen in Bloch sphere. for the boson, because the boson that is affecting the Bloch sphere that is affecting the boson is gonna stretch out to infinity. So this was when in the Bloch sphere, and there is the axiom now. The axiom is a different concept, almost a totally different concept.
What's up?
He's thinking.
Stretch up until R infinity. But this has the same graph as the Fermion. But the difference with the Fermions is that it is not the same equation. I mean, it is the same equation actually, but then the difference is that it doesn't get affected by the Bloch sphere. So, which means there's actually almost no difference with the Fermion and the Axion, now the Photons. Photons are we will set this. Photon is normally put as a moderator for the Fermion, boson, and axiom, which means that similarly with the axiom, it doesn't get the effect of the Bloch sphere. And if we calculate it, I calculated and to like this. The Boson's value that looks like this is very new to me, because what I've searched all in total has never gotten me to this value of boson. The boson, this R, the RS needs to be, this one should be smaller, but this one was bigger, see? And if we write all the boundaries down. Where's the Boson? Oh. Except for the axiom, which is isometric boundary, everything is conformal. Everything is conformal except for the axiom. Do you know why? I think, which is not found out yet. I think that since the axiom is the only one that is not getting influenced by the Bloch sphere, which is in the universe, I think the Bloch sphere, the axiom, why the axiom is only isometric boundary is because everything that is inside the Bloch sphere is conformal boundary, but this Bloch sphere doesn't exist in the isometric boundary, and that means that the axioms don't work in the conformal boundary. Now, that was just an intro, and now we'll get into the quantum Hamiltonian. Ooh. Wrong side. Oh. Marker's dead. Okay. Alive. Oh. Probably very familiar with this, right? Do you know anyone? Anyone knows what this is?
Or is this?
Yeah.
So this is very famous. Not very famous, but famous in the world of quantum mechanics. And this was by Lewis.
What?
It was by Lewis. This guy is the guy that made this Hamiltonian and find Hamiltonian G1 exchanging values with G6, G6, and working in isometric with R1, 2 sticks is bigger than 1. Quantum signal processing was the name for this, and Lewis Szilard was the most intuitive person to have studied quantum signal processing. Since he is very good at studying, he was very intuitive in the thing about quantum signal processing, and he wanted to be the first person to do some kind of thing. And he did some kind of thing, and he found this. The Hamiltonian of Hamilton. Hamilton, he's a mathematician, and Hamilton has with the p theta and the so first he concluded that this Hamiltonian P is same as the 2-6 Hamiltonian, the 3 theta and the gamma mu n times the I h of dd over d. Right? And then he concluded that that is also same as V Hamiltonian P. And then he concluded that Hamiltonian P is equal to the V Hamiltonian P, which is simple, very simple, but very hard. Because, see, finding this is equal to this, everybody found it out, but they didn't think that this would be equal to this. But Leo Szilard wanted to be the first person to do some kind of thing, so he did everything that he could make of, even impossible things, which led him to find another Hamilton of the conformal boundary, which is something like this. Highly
Finish?
I have not concluded my idea and think that this exchanging of ends here like this. Path integral made by Richard Feynman. It explains a lot of the quantum electrodynamics. And the quantum electrodynamics that Richard Feynman studied is included in the Hamiltonian isometric boundary. Isometric as the Richard Feynman's quantum electrodynamics path integral is in the formation of Hamiltonian calculus. So mu right now here is working as a moderator for R1. Right here, R1, it is working as a moderator, and the exchanging value of delta t and Lacamas n is working as an operator of the value. Working as that G6, the G1 and the G exchanging of G1 and G6 is inside the isometric boundary of the double sticked R1, which is bigger than at least 1. So this could be 2, right? So if it is 2, it'll be right, lim G6 is 2, and Hamiltonian 2 stick of minus infinity. Yes. Exactly like this, which is obviously correct. And then there is the expanding to this, there is dx, which is in same as the value, but then there is also going from here, not done yet. This formation is not done. Like this, right? And expanding from this, there is the delta x with another one, theta, this time, mu square I h square, like this, and over square. This is not squared. Like this, right? And the p theta is explained in right here. Expansion of this, and we will put the moderator, which is this right here, and we will put Hamiltonian minus infinity as one stick, single stick, as the moderator, which can be looking like this, right? Expanding this isn't hard because it is just calculation. I thought, wait, oh, this I equal R1 that is bigger than, that is same as 2 double stick Hamiltonians and remember n right here. And here we can use another value in the operation by Liost-Szilard. Right here. This one is RS, but this one is bigger than 1. And the exchanging with the other side going to the radius side, going to the opposite of the radius. One last thing now.
One last.
There is the isometric boundary of this, which is looking good, looking like this. Very professional. Even one, which is already proven. Exchanging with infinite. We'll add on the R going to the other side, and we'll have R going to this side with the delta with what I wrote here. And I didn't know that these two will match. Okay? This guy will become soon deleted. I first gotta write the basic formula. Every quantum mechanics is easy. Everything gets connected at once. It's already proven by professional degrees, and I have done it. And it matches with these colleagues. Exchanging values and Bloch, which I've already coded, I think. Now this one will disappear, and the only thing that will be left is this, but we can do this with the operators. And H zeta, Hamiltonian P, I of H, with R bigger than 1. Because these two disappeared, and since we times that this, we should have the operator. First gonna write the operator as the basic, which says that this one will be smaller than 1 this time. And but this operator was seen R going to the opposite side of the radii, and C 1 minus P minus S. Like this. So the isometric boundary of this is Can we simplify this more? I've tried and I think that this is another simple form because I have used the Hamiltonian. Pretty simple. This is going to the right side. Oh, you wait, yeah, that is it for today, but I will show you something. This one, how I got this, is actually in my steps pioneering to this calculation. In step this one, yeah, this one. In this step, I change the value like this, and wrote it as this, which got me